Okay, let's dive into this. If you've been watching the big picture, you know we're at this really wild point where global energy demand is just, well, it's exploding,
Yeah.
mostly because of AI.
It really is. We're seeing this massive build out of high security AI data centers. It's actually starting to, overshadow traditional office construction in importance.
Yeah, it feels like the race for AI dominance is truly on. And the biggest thing holding it back, reliable power, consistent dispatchable power, 204/7.
And what's so interesting right now is how this huge need for power is lining up perfectly with a big shift in, let's say, political feeling about nuclear.
Ah, yeah.
So we're going deep today on the advanced nuclear sector, looking hard at Oklo Inc. They seem to be right at this intersection point.
Because nuclear acceptance is actually up,
Hmm.
unlike wind and solar.
Yeah, it's quite a contrast. Acceptance for wind and solar has kind of leveled off, maybe even dipped a bit lately. But for civil nuclear, it's seen a pretty significant climb across the board, politically speaking, from around 2016 to now.
That's a huge shift. So our mission today is basically to break down the policy changes, the tech, especially their fast reactors, and the partnerships that are giving companies like Oklo a faster track.
Exactly. We want to distill what's really accelerating things.
Okay, let's start with the demand. You mentioned AI driving almost half the new U.S. electricity demand by 2030. That sounds staggering.
It is.
Well,
Projections show U.S. electricity demand jumping maybe 25% by 2030.
Mhm.
And yeah, roughly half that bump, data centers. And advanced nuclear, particularly these smaller designs, seems tailor-made for this. AI needs distributed, reliable baseload power. You just can't run these critical systems on power that comes and goes.
Makes sense. And it sounds like the federal government gets this too. They're treating it like a national security thing.
Very much so.
So what are the concrete policy steps? Not just talk, but things actually speeding up licensing and getting these built.
Right. It's about cutting the red tape and moving faster. There's been a really coordinated push, think executive orders, new laws focusing on licensing reform. They're setting targets, like an 18-month review window for new reactors and capping the fees. This is huge for companies like Oklo using a combined license approach.
Hold on, combined license. Can you unpack that quickly?
Yeah.
Why does that help speed things up?
Sure. So traditionally, you needed a construction permit first, build the plant, then apply for an operating license. Huge financial risk during that build phase, right?
Yeah, years and billions potentially at risk.
Exactly. The combined license, or COL, merges those steps. Once the Nuclear Regulatory Commission, the NRC, signs out on the design and the site, they issue the COL. It combines the safety reviews, cuts out a big step, and tackles those infamous decades-long delays we used to see.
So it streamlines the whole thing. And the goal is 3 operational advanced reactors by July 2026. That seems incredibly ambitious.
It is aggressive,
Yeah.
but it shows the level of commitment.
Okay, so faster licensing is one piece. What about fuel? You mentioned that's being reframed as strategic too.
Precisely. Calling civil nuclear a national security priority unlocks access to really important government assets. We're talking stockpiles of enriched uranium, even plutonium-based materials. Stuff once seen as waste or purely military.
Stuff we already have.
Exactly. And the key thing is, in advanced reactors like Oklo's fast reactors, this material often doesn't need a lot of costly extra enrichment. Just these existing stockpiles could fuel something like over 3 gigawatts of new powerhouses.
3 gigawatts is substantial. So accessing stockpiles helps with the early fuel supply. But building reactors, even smaller ones, isn't cheap.
Is the federal money, the tax credits, the loan programs enough to really make these first projects viable?
It provides a kind of stability that wasn't there before. Recent legislation kept the investment and production tax credits going pretty far out, actually, through 2033 with a phase-out to 2036.
Okay, that's long-term certainty. And importantly, it beefed up the loan programs office with this energy dominance financing program, specifically for first-of-a-kind projects. It helps absorb those initial higher costs and makes the economics, more predictable.
So the government's basically paving the road, faster permits, fuel access, financial backstops. Now let's pivot to Oklo itself. What makes their specific approach fit these faster timelines?
Yeah, their strategy seems to lean on 3 main things. First, their business model. Build, own, operate. They handle it all and sell power through long-term contracts. Keeps it simple.
Okay, BUO. Got it.
Second, the size and design. They use these micro-nuclear reactors or powerhouses. Small, scalable, perfect for putting right next to a customer like a data center or maybe a military base.
Makes sense. Smaller footprint, easier placement.
Right, and that small size means easier installation, more factory fabrication, less complicated work on site.
And the third pillar is the technology itself, the fast reactor part.
Absolutely. That's kind of the core innovation here. They're using liquid metal fast reactor designs. Now, this isn't brand new, untested science fiction. There's over 400 reactor years of global operating history behind these concepts.
So it's proven physics.
Proven physics, and that allows for inherent safety features, passive safety. Basically, the reactor helps shut itself down safely without complex systems. That means fewer safety-grade systems needed, which simplifies the regulatory review and, crucially, lowers the cost.
That cost piece is key, given the history of nuclear projects. And you mentioned simplifying the design. How does that connect to their supply chain? Are they building these things differently?
That's a huge part of it. Their supply chain strategy is, frankly, quite clever. About 70% of the components for their powerhouse, they come from non-nuclear supply chains.
Really? Like what?
Think standard industrial parts, things from the energy sector, the chemical sector, mature industries, established manufacturing. That means lower costs and shorter lead times compared to specialized nuclear-grade components.
Tapping into existing industrial capacity.
Smart. So are we seeing this translate into actual construction timelines yet?
We are. They've picked Carrot, a big, experienced construction firm, to lead the build for their first Aurora powerhouse at Idaho National Lab. Pre-construction work is slated to start in Q3 2025.
And when do they expect power?
They're aiming for commercial operations sometime between late 2027 and early 2028. So, yeah, things are moving.
That is fast for nuclear. And I saw something about an innovative approach to licensing the operators, too. Something about type ratings.
Yes, that's another really interesting piece for scaling up. Their license operator topical report proposes licensing operators based on the Aurora technology itself, kind of like how pilots get a type rating for a specific aircraft model.
Ah, like a pilot rated for a Boeing 747 can fly any 747.
Exactly. So instead of licensing operators specific to each individual site, you license them for the Aurora design. This could dramatically streamline training and certification for operators at future plants. It supports a much faster, almost franchise-like rollout model. Okay, build, own, operate, small size, factory parts, type ratings. That all points to deployment speed. But the fast reactor tech itself, that seems aimed at solving the long-term fuel and waste headache, right? The thing that's always held nuclear back.
That's the deeper story, absolutely. Let's spend a bit of time on that fuel cycle breakthrough. It's about turning what we call waste into, well, gigawatts of power.
Starts with how inefficient current reactors are.
Fundamentally, yes. Today's light water reactors only use about 5% of the energy potential in the uranium fuel they're loaded with. That means 95% of the material that comes out the spent fuel or waste is actually unused fuel. It's a massive amount of wasted energy potential.
95% unused. Wow. So what do fast reactors do differently? How do they tap into that?
Think of it like this. A standard reactor is a picky eater. It mainly consumes a specific isotope, uranium-235. Fast reactors, because they use neutrons with higher energy, a fast spectrum, are much less picky. They can burn or fission a wider range of heavy atoms, including plutonium and other transuranics that build up in spent fuel.
So they eat the leftovers.
Pretty much. They can effectively use this mix of materials from spent fuel, which standard reactors can't, and importantly, they can tolerate fuel that isn't perfectly pure. This tolerance makes advanced recycling methods much more economically viable. The potential's there to produce fuel from recycled material cheaper than mining new uranium.
Okay, cheaper fuel from recycling. But the scale, you mentioned the energy in existing U.S. waste is comparable to global oil reserves.
That's the mind-blowing part. The estimates suggest recycling the current U.S. inventory of used nuclear fuel could, using fast reactors, unlock the energy equivalent of somewhere around 1.2 to 1.3 trillion barrels of oil.
That's world-changing if it's true. We're basically sitting on one of the biggest energy resources on the planet, and we've been calling it trash.
Essentially, yes. It completely reframes the energy resource conversation. This fuel is already mined, already here. Oklo is clearly planning for this long term. Their fuel strategy has three parts. Access the government stockpiles for near-term needs.
Right, the 5 metric tons for the Idaho plant.
Exactly. Then, partner for commercial supply, like with Centrus and Hexatom for new enrichment tech. And then the big one, build their own long-term recycling capability.
They're planning a dedicated facility.
Yes, a proposed $1.7 billion recycling facility in Tennessee, aiming for production sometime in the 2030s. It's vertical integration.
That's a big investment, but it locks in their fuel source. And does recycling help with the actual waste disposal problem, too?
Significantly. By burning up those long-lived transuranics, recycling can drastically reduce the volume of the final high-level waste. And crucially, it shortens the time frame that waste stays highly radioactive from hundreds of thousands of years down to several hundred years. It makes long-term disposal much more manageable.
Cheaper fuel, vast supply, better waste profile. That's a compelling trio. Okay, so they have the tech, the fuel strategy. How are they doing on actually signing up customers? Where are these reactors going?
They're landing deals in critical areas. A
Mm.
big one is being selected by the U.S. Air Force. They're the intended awardee for the first advanced reactor at a military base up in Alaska.
Alaska makes sense, remote, high energy costs.
Exactly. And that project is key because it'll demonstrate using the reactor not just for electricity, but also for heat and steam. Important for heating buildings in that kind of environment. Shows versatility.
Right. But the partnership that really raised eyebrows was with Liberty Energy, a gas company. How does that work as a bridge to clean energy? Seems counterintuitive.
It does at first glance, but it's actually quite strategic. The reality check for advanced nuclear is the timeline, right? Customers, especially big data centers, need power now, not potentially in 2028 or later.
True, they can't wait years.
So Liberty steps in with its existing gas generation capabilities to provide that immediate, reliable power. It acts as the bridge. Customers get the power they need today, avoiding the risk of them going elsewhere while waiting for the nuclear plant to come online.
Ah, so it prevents customer loss during the build phase.
Precisely. It's an integrated offer. Reliable power now via gas, with a clear contractual path to switch over to clean baseload nuclear power from Oklo once the powerhouse is ready. It's a smart way to manage risk and meet immediate needs. They see it as a scalable model.
That makes a lot more sense. So it's about securing the customer long term. And they're integrating on the tech side, too, with Vertiv, the data center infrastructure company.
Yeah, that's another piece of the puzzle. That partnership focuses on integrating the power source with the data center's cooling needs. Fast reactors produce a lot of heat.
Waste heat, usually.
Right. But the plan is to use steam generated by the Oklo powerhouse to drive chiller systems for the data center. It boosts the overall energy efficiency using waste heat for cooling. It's
Oh.
about offering a more complete, valuable solution than just electrons.
Tailored solutions for specific customer needs. And beneath these specific deals, they claim a pretty big pipeline.
They do. They maintain it's the largest SMR, small modular reactor pipeline out there, around 14 gigawatts total. And they say a lot of that interest is coming from the hyperscalers, the big cloud and AI companies. The demand signal is definitely there.
Okay, so summing up Oklo's position, they seem to be riding these strong federal policy tailwinds, using their fast reactor tech to unlock this massive potential in recycled fuel, and using smart partnerships like the gas-to-nuclear bridge to land customers now.
That captures it pretty well, leveraging policy, unique tech, and pragmatic business strategy.
And they seem to have the funding to pursue this.
Looks like it for now. They raised a significant amount, $460 million gross, in Q2 2025. Ended that quarter with around $683 million in cash and securities. So they appear capitalized to execute on this accelerated plan. The pieces seem to be falling into place.
It's a fascinating convergence. Which brings us to our final thought, something maybe a bit further out.
Yeah, something beyond just the energy production. We talked about the recycling facility making fuel, right? But there's a potentially huge secondary product line hidden in there. Radioisotopes. Oklo calls it atomic alchemy.
Isotopes, like for medicine.
Exactly. Medical imaging, cancer therapies, specialized industrial uses. The process of recycling spent fuel allows for the extraction of a whole range of valuable isotopes. Because fast reactor recycling handles a complex mix of materials, they could potentially produce a diverse set of these isotopes much more efficiently and abundantly than current methods allow.
So moving from scarcity to abundance for these materials.
That's the provocative idea. Right now, a lot of R&D using isotopes is limited by supply and cost. If a company like Oklo can start producing a wide variety of useful isotopes reliably, almost as a byproduct of making fuel, well, what does that unlock?
It could spur whole new areas of research.
It could create an entirely new ecosystem for R&D in medicine and industry, one based on abundance, not scarcity. Think diagnostics, therapies, materials science. It's a potentially massive, high-value revenue stream, completely integrated with their core fuel cycle business. It might change a lot more than just how we generate electricity.
Huh. Turning nuclear waste not just into power, but potentially into new medicines and technologies, too. That is definitely something to think about.